All right, let's look at how you balance chemical equations. So to begin with, we have to consider what chemical equations represent. And here's an example of one. A reaction between hydrogen gas and oxygen gas to produce water. This is basically fire. It's the hydrogen burns in the presence of oxygen to make water as a product. Now, as a reminder, for chemical reactions, you must obey the law of conservation of mass, which means matter can neither be created nor destroyed. So here we have two hydrogens, that's fine. Here we have two oxygens and then one oxygen at the end. If you take this literally, this means one oxygen disappeared, and we can't have that. So we need to fix this in order to show what's actually happening. So that's the balancing the equation. And what we're going to do is we're going to change what's called the coefficients, which means we leave these numbers alone. We leave the formulas alone, but we can change how many of each molecule. We can have 2 of these or 3 or 4 or whatever. So looking at that, we have 2 hydrogens here, 2 hydrogens, that's fine, 2 oxygens and 1 oxygen. Well, that's not fine. So we fix this by putting a 2 here. Now there's 2 oxygens and 2 oxygens, but whereas before the number of hydrogens was fine, now it's not, because now there's 4 hydrogens and now there's only 2 of these. So we fix that by putting a 2 here also, and this would be a correctly balanced equation where 2 hydrogens react with 1 oxygen to make 2 waters, basically is what it is. Or rather, 2 molecules of hydrogen react with 1 molecule of oxygen to make 2 molecules of water. So we can apply this to a variety of situations. I suppose since we got one kind of like this, let's look at another one like that. C2H8 plus O2 reacts to make CO2 plus H2O. We do likewise. We just go through these different elements to make sure you have the correct numbers of each. The hint I will give is save the pure element for last. So 2 carbons, let's make that 2 carbons. 8 hydrogens, let's make that 8 hydrogens. That fixes carbon and hydrogen, 2 carbons, 8 hydrogens. Now what about the oxygen? Let's see, we have 4 oxygens here. 2 times 2 is 4. 4 times 1 is 4 more. So 4 plus 4 is 8 oxygens. So I'll put this 4 here. That way there's also 8 oxygens on this side. There we have a correctly balanced chemical equation. Looking at the homework, we see a variety of similar problems that can be approached the same way. 4 phosphoruses. Great, 4 phosphoruses. There's 10 oxygens here. In order to make 10 here, you got to change the coefficient. You give it a coefficient of 5. And when we deal with something slightly more complicated like this, 1 lead, 1 lead, 1 silver, 1 silver. Well, what about these? Well, these polyatomic ions, we treat them as a single unit. So we see this 1 nitrate right here, and there's 2 nitrates. So, everything looks good except for the nitrates. So let's fix that. There's 2 nitrates. So let's put a 2 here. That way there's 2 nitrates. Well, now there's 2 silvers, so we fixed up by putting a 2 here, and okay, it looks like that got it. So here we can apply the same thing. In fact, you, the viewer, I suggest go ahead and try this one out. Pause it, and then play this video to see the answer. Because in that answer, I will show 1 zinc, 3 zincs. Oh, okay, let's fix that. 3 hydrogens. 2 hydrogens. Oop, that doesn't work. But let's save that pure. I am seeing that there's going to be some other things coming up. You know what? Let's save the pure element for last. Let's actually 1 phosphate, 2 phosphates. Okay, let's make this 2. Oh, okay. Actually, this is pretty simple then. So now we have 2 phosphates, 2 phosphates, 3 zincs, 3 zincs, 6 hydrogen. We put a 3 right there, and we have 6 hydrogen. Alternatively, you could have just put a 3 here and a 2 there, and you would have had the number of hydrogens balanced, and by chance, it would have also fixed the phosphate problem. And the rest of these are going to go in pretty much the same way. Now, for some of these, you may see a fairly difficult circumstance come up. And so rather than show the rest of these, I want to go through another more complicated example, one that requires what's called a fractional coefficient. So consider this. CH3OH, that's called methanol, burns in the presence of oxygen to make carbon dioxide and water. Yeah, notice, by the way, when stuff burns, it always seems to make this carbon dioxide and water, or at the very least water as a product. But at any rate, this is the unbalanced reaction. Unbalanced because, look, there's 4 oxygens, 3 oxygens, 2 hydrogen, 4 hydrogen. So we got to fix that, and here we go. We fix that by taking, well, we'll save the oxygen for last. Let's do the other ones first. 1 carbon, that's fine. 4 hydrogen, 2 hydrogen. Oop, that doesn't work. So let's make this 4 hydrogen also. By putting a 2 here, I now have 4 hydrogen to match the 4 hydrogens. So hydrogen's good, carbon's good, now for oxygen. Having done that, there is a total of 4 oxygens on this side. We need 4 oxygens over here too. Problem is there's 3. What do I do? If I change the number of this oxygen, that means I have to put a 2 in front of this or something, and that changes all these, and it's going to make us fix the hydrogen and the carbon, and you're going to go back and forth in an endless cycle. Instead, let's change the number of this. So we have 4 oxygens here. We need 4 oxygens here. How do we get 4 oxygens? Well, I have this, so I need 3 more. If I could have 1 plus 3, that would make 4 oxygens here. So how do I make this 3? I'm going to say there's 1.5 of these. Right? Wouldn't that work? 1.5 of this is 1.5 of these. That's 3 oxygens. Plus 1 more is 4, and there's 4 oxygens here also. This would make it work. Too bad you can't have a fractional coefficient in your final answer, but that's okay. Your solution, if you use this fractional coefficient, you multiply everything by 2. Multiply by 2. And when you do that, your final answer, I'll put that down here, will be 2 of these, 2CH3, oops, a little messy there, but you get the idea, times this by 2, 3 oxygens, and that produces, let's see, this times this by 2, 2 carbon, oops, 2 carbon dioxides. Let's see if I have a whiteout handy. Yes, I do. Two carbon dioxides, and got to times this by 2 also, 4 waters. That would be how you use fractional coefficients to take what would be rather difficult to try and turn 3 oxygens into 4, and we check at the end. How do you know if you're right? 2 carbons, 2 carbons. Let's see, 4 hydrogens times 2 is 8. 8 hydrogens here also. 2 oxygens, 6. So this is a total of 8 oxygens. There's 4 oxygens here and 4 here, so that's also 8. So 8 oxygen, 8 oxygen. Good, that's how we know that part is done correctly. So that sort of thing is pretty well what's going to trip some people up, especially here where you have to count this and this together. But that is how you handle these difficult sort of reactions. Now, I suppose there is also another reaction we could potentially work with. Let's see. I can do a reminder of this one from the notes. Let's see. Reaction of ammonia and oxygen at 1,000 degrees Celsius. So let's see. Ammonia plus oxygen to make nitrogen monoxide and water. Let's go through the same process again. You, the viewer, I suggest pause this video, work this out, and then press play again to see how this went. So the process, one nitrogen, that's fine. 3 hydrogen, 2 hydrogen, that's not fine. So I'm going to need to balance these, and my favorite trick is to take this 3 and put it right here, and take this 2 and put it right here. That way I've got 6 hydrogen and 6 hydrogen. Now by fixing the hydrogen problem, I just messed up the nitrogens. You'll notice we got 2 nitrogens here and 1 here, so we fixed that. And now I save the pure element for the end. Here we go. There are 2 oxygens here and 3 oxygens here, so there is a total of 5 oxygens. I need to somehow get 5 oxygens here too. In order to do that, I will say, one O2 has 2 oxygens, 2 O2s has 4 oxygens, 3 O2s has 6 oxygens. So I need more than 2 and less than 3, so I'll say 2.5 oxygens. 2.5 of these will give me 5 oxygens. Well, just as before, I can't have a fractional coefficient in my final answer, so I need to fix that by timesing everything by 2. And so let's do that. So we multiply everything by 2, and that gives us the final answer of 4NH3 plus 5O2 makes 4 nitrogen monoxide plus 6 H2O. And notice this cannot be reduced. 4 to 5 to 4 to 6 ratio. You can't reduce this. This would be the final answer right here. And how do we know what's right? Well, let's check. 4 nitrogen, 4 nitrogen. 4 times 3 is 12 hydrogen. 6 times 2 is 12 hydrogen. So 12 hydrogen on each side. 10 oxygen. Well, 6 plus 4 is 10 oxygen. So we have the correct the same number of each element on each side. And that should be basically what we're looking for in order to make it work. On the homework, let's see, let's look this over, see if there's anything that looks kind of like this. It looks like this one will require a fractional coefficient just off the top of my head looking at it. I can see a couple that will actually. Let's see, 1 potassium, 1 nitrogen, 3 oxygens, 4 oxygens. Okay, so for this one, there's 3 oxygens here. What would it take to make 3 oxygens here? We don't want to mess with this because that'll change this. Here we can change just the oxygen. What if we had half an O2? If this was just 1 oxygen, that'd make it work, wouldn't it? There'd be 3 and 3 if this was just 1 oxygen. So let's do that. So we'll have half of an O2. Or, alternatively, you can just put a decimal. 0.5. That would work. 1 potassium, 1 nitrogen, 3 oxygens, 3 oxygens. Because this is 1 oxygen now, half of an O2. Well, okay. Since we can't have that, we fix that by multiplying everything by 2. So your final answer is 2, 2, and then this times 2 is just 1, so I'll just wipe this out. And there we go, 1 oxygen. Now this is balanced. Looking at these other ones, let's see, this looks like a similar one right here. This will also require a fractional coefficient because 1 carbon, 3 oxygens, 2 oxygens. This would work well with half of an oxygen. This would make it work. And then in order to make that happen, we gotta, so now 1 carbon, 1 oxygen plus 1 more makes 2. 2 oxygens here, 2 oxygens here. And then we fix that by timesing everything by 2. So that times 2, half times 2 is just 1. So there we go. We just have the O2 again, and this becomes a 2. So 2 of these, 1 of these, 2 of these. And having seen that, honestly, all the rest of these, regardless of how complicated they are, essentially follow the same rules. So there's really not too much to add to this sort of thing. If you follow along with the rules covered here and here, that pretty much covers everything you need to know for chemical balancing. So there we are. Happy studies.